Okay, let's get started. So this should be lecture 25, if I'm keeping track. So few things. So I put a revised course outline on the website, which you'll find. Second, I'm sorry that for a few days it was showing that there won't be a class today, but I need to have a class today. In the next few weeks, there might be a few missed classes because of some public holidays and all. Actually, that is all showing on my webpage. Finally, you know that next week on Thursday, there will be the second quiz. Okay, or you should know, that's also on the blog. Okay, are there any questions about what we did last time? Yes, Shayan.
So, when we fix the one of the coordinates to so one of the components of phi to be a, and the rest of the components are 0, 0, 0. And we said those n minus components have some SON minus ON minus 1 symmetry.
Yes.
But since we have fixed the norm and one of the components is a,
We haven't fixed the norm.
but phi I equals to a square.
No,
Right?
no, no. I think you're mixing up two different things. Phi I does not have to satisfy that phi I is equal to a squared. Phi I classical has to satisfy that phi I classical is equal to a squared. The classical solution has to be a vacuum solution. The configuration in the path integral doesn't have to be anything. The path integral is a sum over everything. So classically, that means that we choose phi classical to be this, and then we write phi I is equal to phi I classical plus eta. And that's how we get the decomposition that you just mentioned. But phi I does not satisfy any constraint like phi I is fixed. Yes.
In the examples where U1 symmetry was completely broken down, and also in where SU2 was completely broken down.
Yes.
And in those examples where we parameterize the field, the total field as generators of the symmetry multiplied with the classical solution and perturbation in that. Like in that parameterization gives the axionic Goldstone boson.
Correct.
So, like, could you articulate that rule, like how to get the
Good. I'll articulate the rule a little bit better today, and I put a small para in the notes. But unfortunately, the full detail of it requires this, what I said, understanding of coset of group manifolds, which requires a little too much math preparation. It's not difficult, but it will require at least a full lecture or two just on that. And I don't want to go to the general groups here, because in practice, first of all, if you need it, you can always pick it up later from some other source if you need it in your research. And secondly, you may not need it because in most of particle physics, we only work with very small groups like U1 and SU2. But I'll still articulate it for you now. So let's do a concrete example. We did yesterday a case where ON breaks to ON minus 1. Exactly the one that just now I was discussing, which Shayan asked about. This case you remember from last time. So in this case, this has n minus 1 over 2 generators. And let's call them TA, where A goes from 1 up to n minus 1 over 2. This subgroup has n minus 1 into n minus 2 over 2 generators. And now the point is, this is a subgroup, so it comes from a sub-algebra of this one. And since these are the generators of the algebra, I should be able to pick a subset out of these, which are the generators of that sub-algebra. Okay? So, what I'll do is the following. I'll break TA into two sets. The whole collection of TA. First of all, I'll write a set T capital A, where A goes from 1 up to n minus 1. And then I'll put Tm, where m goes from n up to n minus 1 over 2. And if you count this total number, it's exactly that. So the idea is, out of all the generators of On, these many are generators of On minus 1, and these are extra. Okay, people are looking very puzzled, but it's not very difficult thing to understand. If you are puzzled by these things, try a simple example yourself. Let's, for example, look at O4. Okay, or O3, even easier. So, okay, we can even say it in words. Supposing we have an O2 subgroup of O3. What's the dimension of O3 from this formula? 3. It shouldn't have taken you this long to calculate it. O3 is the group of rotations. Surely we'll know there are 3 rotations. What about O2? What's the dimension? So O2 is 1 rotation. Okay, so O2 is the subgroup. That means from 3 rotation generators, I can pick one of them which is an O2 generator. Say the last one. Then the first 2 are leftover generators and they come in this family. So I've just divided TAs into 2 groups. One are the subgroup generators, the others are just some generators. These don't generate a group, because if I take the commutator of 2 of these, it might be one of those. For example, if this is the Z generator of O3 and these are the X and Y generators of O3, then the X and Y commutator leads to a Z rotation, that you know, I hope, and that's there. So it doesn't form a subgroup, but it just forms a subspace in the algebra. Okay, so this split I make. Now this n-1 is exactly the number of broken symmetries in going from On to On-1. By definition, it's the difference of this number minus that number, and it is n-1. I did this yesterday. Okay, so we can parameterize the Goldstone bosons by picking this set of generators out of the full set. So that means I can take my field phi I and parameterize it as e to the I t a theta a of x times 0 dot 0 and a plus sigma of x. Conventionally we put √2 here. If this notation confuses you, again please work it out for O3 where the T's are the Pauli matrices, half the Pauli matrices. Then you can work out this thing. This is a matrix because it's exponential of a matrix, so it's also a matrix. So it acts on a vector to produce a new vector, and that's this. So that means now I have parameterized the components of this n component set of scalars as a group, a kind of a group element. So these are group elements. This is a group element of On times that thing. Now if I insert this into the Lagrangian, I should find, and either I'll put it in the notes or I'll leave it. Maybe I have left it already as an exercise to do in some simpler case where it's, so this case is the one where these are all real and this is On, but I could also make it O3 or I could make it SU2 and it would be a little simpler. And when you do this, what you'll find is that the Lagrangian simply becomes half del mu theta A del mu theta A plus half del mu sigma squared. Up to now it's just the kinetic term. Then a mass term for sigma, which is actually mu squared sigma squared. Okay, the original Lagrangian had plus mu squared by 2. The final Lagrangian has minus mu squared. This is similar to all the cases we have discussed. And then some cubic and quartic terms which are of the form basically something of order plus order sigma cubed and sigma fourth. So there are no potential terms depending on theta. This shows me precisely that theta are Goldstone bosons. Okay. Now, why did this Lagrangian obligingly take such a nice form where only sigma appears and these thetas don't appear? Because the Lagrangian has a global invariance under the group On. That's the original Lagrangian in which I've inserted this. Okay. So if I insert a field which has this factor in front, then this factor will cancel in the potential terms. Okay, that's the statement that it has a global ON symmetry. Because a global ON symmetry is what can remove such a factor. Only the constant part of it, but that's enough to remove it from the potential terms. And therefore, these thetas won't have any potential. This is just another way to say everything in words, but I see people nodding. So just try and work out these details for yourself. There are enough exercises in the notes that you can work them out for SU2 or O3, but you have to be very careful. If it's ON, then the fields are real to start with. If it's SUN, then the fields are complex. When they are complex, then you have to do something slightly different. So you may get one more field here, or you have to do something different. So I've given you various hints of how to do things, so you just have to work it out. The most detailed exposition of this problem, I believe, is in the textbook of Weinberg, volume 2. Weinberg has three volume textbook on QFT. So in volume 2 of his textbook, the whole picture of spontaneous symmetry breaking and coset spaces, as far as I know, is worked out, and Weinberg himself actually wrote a lot of research papers on this field. Okay, because after all, he was one of the people who worked with this thing, which played a role in the standard model. Okay, so that's about your questions. Any others? Okay, so today we are going to talk about a very nice topic, and the way to introduce it is the following. So there are two curious problems, one motivated by experiment and one motivated from theory. The experimental problem is that weak interactions are short range. I'm sure you know this since you have had last year a course on nuclear and particle physics. That should be enough to tell you this fact. Okay, so if they are short range, then we can try to see in what way could they be similar to electromagnetism. Well, short range is one way in which they are not similar, because electromagnetism is long range. That's why light from the sun can travel far enough to reach here without significant attenuation. But if there was any weak interaction kind of light, analog of light, it would not be reaching here. It would travel to a very short distance, which is the length scale of the weak interactions. This is an experimental fact. Okay. This is also why nobody had found the weak interactions till the 1960s, or whenever they were actually found, because for centuries people were studying forces of nature and they only could find gravity and electromagnetism, and both are long range. That's why they could find them. To study weak and strong interactions, you have to have enough experimental ability to penetrate inside the atom. So the field of subatomic physics was born in the last century, and in subatomic physics, indeed, you realize that there is an interaction called weak interaction, and it's short range. Okay. Now, people from Schwinger onwards, so Schwinger was one of the earliest to make this proposal in the 1950s. Glashow came up with another proposal in the early 1960s. Said maybe weak interactions are mediated by vector fields. So they had reasons, which I won't go into here, why it would be good if weak interactions can be mediated by the exchange of vector particles, just as electromagnetic ones are. But this proposal is dead almost instantly, because vector fields, the only consistent coupling we know of vector fields is the Yang-Mills coupling, which we have been studying all this time. I think you know the reason. The reason is that this has gauge invariance, and because of gauge invariance, we hope we can remove the unphysical states of the vector fields and have a unitary theory. We spent a lot of time arguing this. It works exactly the same for non-abelian or abelian. We need some gauge invariance, and Yang-Mills is the way to have gauge invariance. Okay, but then if we have gauge invariance, then there cannot be a mass term. Because this clearly breaks any sort of gauge invariance because of the inhomogeneous term. Even if you try generalizing this to Yang-Mills by putting an extra index here, it won't help because there's an inhomogeneous term always in the transformation of A in a gauge theory. So this violates gauge invariance, but as soon as this happens, then therefore the force is long range. At least so people thought. Because when there's no mass, the force is long range. I don't know if you have really learned this basic fact of QFT or of any physics actually, that if a particle has a mass m, then the effective distance over which it can propagate is 1 by m. Okay, so if it has a mass 0, then it's long range. But weak interactions are short range. So as a result, these people wrote some papers, but nobody could go beyond what their suggestions were because their suggestion had a fatal flaw in the form of long range nature of Yang-Mills particles, while at the same time the force should be short range. So therefore, the idea that these interactions are mediated by vector fields didn't seem to work. The problem is if we assume they are mediated by scalar fields, that also doesn't seem to work for other reasons, experimental reasons, and so then there was no theory of weak interactions at all. And this is how the 1960s started. Okay. Yes.
So what do you mean by the average propagation is about 1 by m?
Just what I said.
No, like particle is created and destroyed in that?
Yeah. No, it's not destroyed. Okay. I think that statement probably is best associated to a wave. But if you want the particle form of it, well, it's the difference between having a propagator 1 over p squared and a propagator 1 over p squared minus m squared. Right? This is the propagator of a massless particle. This is the propagator of a massive particle of mass m. Okay? So if m is significant, then when you put this in the amplitudes, you'll find that the amplitudes are highly suppressed as long as the distance is more than 1 over m. This is in Fourier space. Now you have to, if you want to understand the interaction in position space, you have to Fourier transform this back to position space. And then it's a standard statement of Fourier transform actually, that if this function goes like 1 over m for small p, which it does, then the Fourier transform is damped for large x. On the other hand, this function at small p grows without limit. Okay, this one stops growing. As p goes to 0, it saturates to a value 1 by m squared. This doesn't saturate. The fact that this doesn't saturate in Fourier transform space says that x can be as large as you like. That means that means the amplitudes that you calculate in field theory are significant over large distances. Propagation from here to 100 million miles away is still significant. That's not true with this. It's very easy to work out right now. I don't have the thing in my mind, and also I don't want to spend the time on it, but this is a standard result. You should think it over. Okay. So this was the paradox. Now, for the first half of the 20th century, nobody knew about this paradox, and nobody knew what to do about it, and nobody cared very much, because for some reason, although people wanted a theory of weak interactions very badly, they somehow didn't like this very theory-oriented approach of starting with QFT and trying to make some vector. They wanted to build it from experimental data, to discover the theory from experimental data, and that's not this approach. This approach is to say, well, vector particles are good as mediators of forces and they should have gauge invariance. So that you know, people might say, no, why should they? Vector particles having gauge invariance, who cares about that? It's just a mathematical fact. How do we even know it has anything to do with physics? You haven't made the argument. So, at this point came Mr. Higgs, Professor Higgs actually, and there's a little history about Anderson's contribution, which I might tell you if I have time another day, but today I want to get directly to this. And he asked the following question. The question, okay, so that's one paradox. The short range nature of weak interactions means that vector particles are not very suitable to describe them. The second problem is more of a theoretical problem, which is that Goldstone bosons are bad, at least in particle physics. precisely because they are massless, they are long range, and scalar, but they are scalar particles, they are not vector particles. In this case, it's not that you can't give them a mass, it's that they don't have a mass because you start with some Lagrangian with a symmetry, and when you spontaneously break the symmetry, Goldstone's theorem says they don't have any potential. Okay. Now, if you add a potential by hand after breaking the symmetry, then they will have a potential or a mass, but now they won't have the original symmetry. Okay. So, in some sense, Goldstone particles are also something that seem very undesirable in nature. And again, they come from a somewhat mathematical motivation of spontaneously breaking a symmetry. It's a beautiful idea. It leads to some coset of On over On minus 1. But why should an honest physicist care about such ideas? In fact, this is the reason why they shouldn't care about such ideas. They are massless. They don't, they would have, if there were any in nature, they would have been found. Okay. So, two problems. And somehow both problems cancel each other out in a way that was found somewhat by accident. And the question that Higgs asked was, what if I take a spontaneously broken symmetry theory, scalar field theory, and couple it to a vector field, so that the symmetry which is spontaneously broken goes from being a global symmetry to a gauge symmetry. At least you can say, well, we haven't tried, so let's do it. And see what the resulting theory is. And so I'll write the theory, and you will recognize that every feature of this theory you have already known. The only thing you haven't probably done is to write down precisely this theory and study it. So let me write it and then ask you if you would agree that you already know this theory very well. It's simple putting together of things we have done. Supposing A was 0, then this is not there. Then this is del phi star del phi, and this is a famous Mexican hat potential. So this is the spontaneously broken U1 model which we discussed time before last actually, in quite detail. So that's it. On the other hand, if we want to couple this to a vector field in such a way that the result has full local gauge invariance, then we must use this minimal coupling or covariant derivatives. This also you have worked with. So this has full gauge invariance. And what's the gauge invariance? A mu goes to A mu plus del mu lambda, and phi goes to e to the I, so del mu lambda of x, e to the I lambda of x, e to the I e lambda of x. Normally we write the phase invariance without an e, but now once we couple a gauge field, it's natural to put an e because it's the parameter that we can tune to 0 to take away the gauge field. So it's the strength of the coupling between the scalar and gauge field. And we know from electrodynamics that that strength is exactly the electric charge by definition. Yes, phi. And I should just check my notes to see that my signs are correct. That's always an issue. According to my notes, they are correct. So I put a plus here. So I get minus IE del mu lambda. And here from differentiating IE lambda, which is up in the exponent because phi transforms like this, I'll get plus IE del mu lambda, and they'll cancel. So inside the covariant derivative, the effect of these two cancels each other out. This we already know. We have done this several times. Okay, but the new thing is, we always said this is some potential V of phi star phi. Now we have chosen the potential, and it is of the inverted well type of potential. So it is going to spontaneously break the global symmetry. Question is, what does it do to the gauge symmetry? It's a different question. And in fact, it's a very important different question because, as I've told you many times, gauge symmetry is not just global symmetry converted to gauge. It is actually a redundancy in the description, saying that when I perform those transformations, I'll write them again here, I get actually the physically same configuration. I'm not sure if you have grasped this point, and so maybe I'll repeat it once right now. A global symmetry relates to distinct physical situations. So for example, me facing this way and me facing this way are not facing the same way. Okay, but the physics of me facing this way and this way in a vacuum in an empty universe is exactly the same. That's what the global symmetry says, rotation invariance. Okay, gauge symmetry, however, says that me facing this way and me facing this way have no cannot be experimentally distinguished at all. They are one configuration, just giving it two different descriptions. That's what we mean by redundancy. So we'll see how that plays out. Good. Now, how are we going to analyze this Lagrangian? Well, the good news is we already know what to do, because we certainly should not think. So now if we are going to do a path integral, we'll be integrating over a's and phi's. But in order to integrate over phi's, we certainly must shift phi by a classical solution again. And the classical solution again must satisfy phi star phi equals a squared. So in order to do that effectively, we'll parameterize phi as we did a couple of lectures back by its radial and angular parts. Okay, and then we'll write r of x as a plus eta of x. Or maybe, yeah, maybe I keep making this mistake. It's not a, right? It's 2a is root 2a. 1 by root 2a. Whatever it should be. I should check my notes to see if there are any mistakes like this, but you get my point. Phi star phi has to be a squared. So r squared by 2 has to be a squared. So r is root 2a. Okay, whatever it is, I shift it by eta, and now I insert this as well as this into this Lagrangian. And it can't be very difficult because I've done this exercise before when a was not there. The only new thing is the presence of a. This term is not going to be affected, so I'm not even going to write it again. This term is always there. It doesn't care about what I'm doing. The remaining terms are easy to write down, and when we see the result, we'll realize that we needn't even have done the work. When I put a square, I mean del mu eta, del mu upper eta. I hope that's clear. Then there's a familiar physical mass term for the eta fluctuation. Then there's mu root lambda eta cubed. Then there's minus lambda by 4 eta 4. These are not surprising because these are the terms which we already had without the gauge field. We've already done this calculation and we've already got this answer for the fluctuation of r. Now we have to do the terms which involve theta and or a mu, which we haven't written yet. And what are they? Well, they are plus a squared del mu theta minus e a mu. So I warn you, there might be some root 2's wrong in my existing notes. Plus 2a eta, and also in today's lecture, but I'll fix everything as soon as I can. And that's the answer. Now, why is the answer obviously correct and was easy to predict? What does it look like when a mu is 0?
The previous result we have
Exactly, we already obtained the result that there is del mu theta kinetic term. There's a derivative coupling del mu theta squared times eta, and also del mu theta squared times eta squared. All these we derived earlier. All we have done now is that every time there's del mu theta, it should be accompanied by minus a mu. And why that is so is also obvious, because when I shift a mu by del lambda, it's cancelled by shifting theta by lambda. Why is theta shifting by lambda? Because theta is in the exponent and phi shifts by e to the I lambda, like that. So therefore theta should shift by e lambda. So this clearly has a visible symmetry under theta going to theta plus e lambda, and a mu going to a mu plus del mu lambda. these effects just cancel. I'm sorry, there's an E everywhere. So actually this is nothing but the minimal coupling prescription made in the language of theta rather than phi. For phi, the minimal coupling was del mu minus I A mu, which we had here, I E A mu. But now, once we write this as exponential of I theta, it becomes just del mu theta minus E A mu, not E A mu times theta, but just E A mu. Okay? And the symmetry acting on theta is like an axionic symmetry, but local, arbitrary function of x. Very good. So this is my Lagrangian that I get by simply starting with this and inserting the correct vacuum expectation value of phi. Nothing unusual. Now I want to understand the physics of this Lagrangian. And now I see something very amusing. Supposing I redefine the field A by shifting it, now this looks like a gauge transformation with gauge parameter theta over E. But I'm thinking of it as a field redefinition because remember theta is a field of the theory. So I'm shifting one field by derivative of another field. I'm allowed to shift to redefine fields. There's no sacred basis of fields. I can always redefine fields and physics should not care. But in this case, the effect of this on the F mu nu term, which I didn't write, minus 1/4 F mu nu. There's no effect of that shift on this term because this term sees it as a gauge transformation and it says, well, I'm invariant under all gauge transformations, so I won't change. Okay, these terms don't have any A, so they don't change. In each of these terms, that shift just removes del mu theta because this shifts by 1 over E del mu theta and the shifted term cancels this. Okay, and what's the result? The Lagrangian is whatever it was minus mu squared eta squared minus these cubic and quartic terms of eta, and then these three terms but with only a mu surviving and theta gone. I've just eaten up theta completely. And what are the terms? The first one is plus a squared e squared a mu. The second one is plus twice a e squared eta a mu. And the third term is plus e squared eta squared a mu. So this is the final Lagrangian. So this is the answer to the question, what do I get if I couple a scalar field with a spontaneously broken continuous U1 to a vector field and then expand around the correct vacuum. So let me remove all the mess. This calculation is absolutely easy to do, so there's nothing new in the calculational part, but the answer is very bizarre. So first question in this tool, when you look at this is, where is the Goldstone boson theta? Answer? We had a Goldstone boson in our theory. Where is it now?
It was massless, it's gone with the original.
It was massless doesn't mean that it's not there. Huh? It was there and massless. Now is it there at all? Do you see any theta in this Lagrangian? No. So it's gone. It's disappeared from the theory. There is no Goldstone boson in this theory. Before it was massless, I agree, but it was there. It was very much a physical field. It had a kinetic term and it had interaction terms. So it was very much there. That's before we coupled it to a gauge field. After coupling to a vector field, it's gone.
But if it vanishes, one more freedom should come, one more.
Yeah, and it has. So the second question, thank you, that's absolutely correct. It can't, it's one degree of freedom, it can't just go and disappear. But something else has happened. What is this term? It's a mass term for the gauge field. Not only that, you can check for yourselves that is the correct sign of mass term because the space components have a minus sign, which is the correct sign. The time we won't worry about. because time component always is sick. That gives that non-unitary behavior, but somehow we are hoping that that will go away. Why are we hoping it will go away? Because look, we started with a gauge theory. We actually didn't do anything except expand it around a vacuum. We never broke the gauge invariance. The gauge invariance was there, it's still there. It's just hidden. It's no longer visible that there's a gauge invariance, and in fact this mass term naively seems to break it. But really all that happens is that there was a field theta which was spurious, and by shifting A by that function, I removed theta. That's all that happened. But A is massive. Now, I'm not sure that you learned this in QFT1, but would have been nice. It so happens that in a Lorentz invariant theory, a vector field has two physical polarizations. If its mass is 0, and it has three physical polarizations. If its mass is non-zero. This is a direct result of analyzing the Lorentz and Poincaré groups, which are the symmetries of QFT. I gave some talks on these groups in this Harishchandra series over here in December, but probably many of you were not around. But this is a standard result, and this result you also know from an experimental fact that the electromagnetic wave is transverse. It has no longitudinal polarization, but a generic wave associated to a massive vector field also has a longitudinal polarization. So acquires, and that's the third one, longitudinal polarization. So what has happened in the end is the Goldstone boson has become the longitudinal polarization of a vector field. It has transmuted. The correct Lagrangian is this, and we can read off the physics of the theory from this Lagrangian. We can even pretend that we didn't know how this Lagrangian came. Somebody gave it to us. In that case, we would say, look, this describes a vector field with a mass term. The vector field has cubic and quartic coupling to some other scalar. That other scalar has a normal mass term and some self-couplings. And we know enough physics to analyze this, except that we warn you that this mass term is going to make the theory non-unitary because it's not gauge invariant. Now you answer, aha, yeah, it doesn't look gauge invariant, but it actually is, because I got it from a gauge invariant theory and I never did anything that broke the gauge invariance, so it must be still gauge invariant.
This, like, how is it gauge invariant if there is mass term, right?
It's a very deep issue. I advise you to give it a few days, think it over, read about it.
Also, how do you...
It is gauge invariant. That's the whole. It was always gauge invariant, so it's still gauge invariant. Yeah.
Is it because of those extra E terms within those brackets of eta 4 and eta?
Not really because of, but what is true is that all these coefficients are correlated. If you change any of them, then it won't be gauge invariant. The fact that it came from a gauge invariant theory has already determined all the terms, because the original theory only had E and A and lambda, 3 parameters, and all terms in this better be dependent on that. For example, mu squared is nothing but lambda A squared. Okay, and all these coefficients depend only on E, A and lambda, and again this and this are all correlated. The same E has to appear in all three. I can't put some E here and some E prime here and claim this is a gauge invariant theory. What actually happens if I make a gauge transformation is that A mu will be replaced by A mu minus del mu of lambda plus del mu of some lambda. Well, that will just bring the Goldstone boson back. Okay, but now I won't be able to tell you what is the spectrum of the theory, because there will be an A mu, there will be a theta, Goldstone boson, and in this term there will be a cross term A mu del mu theta, which is linear in both fields. So it's very difficult to extract any physics from it. The only thing you can say is, well, whatever the physics is should be the same as in this choice of gauge where the theta is gone. So therefore, theta is effectively gone anyway. However I want to look at it, theta is not there. It was there, right, till I shifted A. Supposing I never shifted A, theta was there, but it was always a spurious field. If it's a field which I can remove by shifting A, then it's really not there, though it looks like it's there. This is the trick of how gauge invariance works.
So you said that the Goldstone boson has become the longitudinal boson.
Effectively, I mean, it's not really become, it has gone away and the gauge field has acquired a mass, therefore it has acquired a longitudinal mode. It's not so simple as saying the Goldstone boson itself is the longitudinal mode, although there is a way of describing that also. If you get into details in advanced particle physics, this is something that people do. But it's not necessary to think of it that way, because why? The Goldstone boson was massless, the vector field was massless without spontaneous breaking. Now actually the Goldstone boson is gone, so that massless particle is gone. The vector field is no longer massless, it's got a mass. How did it get a mass? This was actually the kinetic term of the Goldstone boson. You've forgotten perhaps, this was del mu theta minus E A mu whole square. So without A, it was the kinetic term of the Goldstone boson. But since the Goldstone boson couples minimally to the vector field, shifting the vector field takes it away. It's very, very subtle. It took people, the smartest minds of that time didn't get it. Weinberg was working, Salam was working, Glashow was working, Li and Yang were working on this subject. None of them got this. And Higgs came from essentially out of the blue and wrote down this kind of toy model, basically this model, and said, well, look, there's a mass. And that's not all, there's a mass, and there's also a real scalar field left over at the end of this procedure. And this tells us that if we want to add a mass to a vector field in a gauge invariant way, we need that scalar, because this scalar actually combines with the Goldstone boson to give me the original scalar field, which had the spontaneously broken potential. So I needed to couple a scalar field, complex scalar field to the vector field to get this Lagrangian at all, right? And once I've got the Lagrangian, although Goldstone has disappeared, this is the radial fluctuation. This has not disappeared, it's very much there. Okay, and the eta field has a name. Well, it's a field, it's called the Higgs field. And if you quantize the theory I've written here, which is not difficult to quantize, then this field describes a particle, and that particle is called the Higgs particle, or Higgs boson, as more popularly. Now, of course, you will point out that I'm bluffing little bit, because this is not the Lagrangian of standard model, nor was the original one, because I've done a U1 example. So this is actually also what Higgs did first. He did a U1 example, but this U1 example can be easily generalized to SU2 or SUN or ON or any other example. The key point is, whatever number of symmetries are spontaneously broken in the absence of gauge fields, those symmetries get absorbed by that many gauge fields and make them massive, and all the Goldstone bosons disappear. That's the kind of bottom line. And that's the Higgs mechanism. So this is the Higgs mechanism.
So
Yes?
if we again make a gauge transformation here, then we will get the same Lagrangian we started with, but with theta replaced with some lambda.
Yes, so you can call that theta as well.
So have we chosen a gauge here by doing this?
In a way, it's like choosing a gauge, that's right. But in this way, you're absolutely right, but in a way, we were forced to do it, because let's think how life would be if we didn't do it. So, before shifting A, we had a term like del mu theta minus E A mu squared. So this is del mu theta with a constant in front. So this is del mu theta, very happy. We say, okay, this is a Goldstone boson kinetic term. Okay. The last term is E squared A mu. We say, okay, this is a mass term for the gauge field. Now we have a massive gauge field and a Goldstone boson, but there's a third term, which is the cross term. Theta, right? Now, whenever we've seen a Lagrangian, we have never yet seen a Lagrangian whose quadratic terms are not diagonal, which have one field coupled to another field. Okay, what does such a term mean? It's not an interaction term, right? You agree? Interaction terms are cubic and higher. This is a quadratic term. But it's not diagonal, it's linear in both the fields. That's a very strange thing. How will we find the propagator for such a system with this sort of quadratic term? Can you think? For that we have to take the differential operator O that acts between the pair a mu and theta and the pair a mu and theta, the O in between. Remember, in path integral we always consider that O and then we need to invert it. Okay, but now O will not be diagonal, it will have one part. So let's actually try to guess what is O. So in a basis a mu and theta, O, a mu and theta, then O should be the matrix m squared eta mu nu, because these indices are contracted. So it is this. This is a 4x4 matrix acting on these 4 components. On theta, it's box, because by partial integration I can bring this here. So it's theta box theta, so it is box or minus box. Okay, this would be fine. Then det of this thing is det of this times det of this, but it's not the whole story. This term says that I have minus e here and I have e here. E del mu and e del mu here. Yeah. So this is my O operator. Yeah, because it connects this A to that theta, so it's a non-diagonal term in O. Okay, now I'll stare at this and I'll say, okay, maybe I can calculate the determinant and try to figure out how to do the path integral, and somebody else will come along and say, you fool, why don't you just shift A so that theta goes away, and then you don't need to do all this. This is gone, this is gone, this is gone. There's only this 4x4 block, and this is an easy matrix. You can easily do it. So the basis in which theta is gone is the easy basis to analyze the theory. Any other basis in which theta is there is the same theory, but theta is like a spurious field which makes your analysis more difficult. Not saying you can't do it, it's just more difficult. And so gauge invariance is concealed in this subtle way that actually you can have any amount of theta, including no theta, but the spectrum of the theory, that means what are the actual excitations, is clearest in the basis when there's no theta. It's not that gauge invariance is gone, it's just that we pick a basis where there's no theta to analyze the theory. It's very, very subtle, and it's still very confusing to many people, including, I would say, myself, but that's what it is. And in one go, they solved both problems, no Goldstone bosons in the theory, and a massive gauge field, which therefore will be short range. And how much is the mass? The mass is E squared times A squared. So because of the vacuum expectation value, there's this, and because of the gauge coupling, there's this. So you can see that it's a phenomenon which would not have arisen without a vacuum expectation value, would not have arisen without a coupling of the gauge field to the scalar. Both are implicated in this mass. Okay, this is the one that carries dimension of mass, because remember phi star phi was equal to was minus a squared was the potential. So a squared has dimensions of mass squared. Okay, but the mass is proportional to A but also proportional to E. Now E we know, but a priori we don't know. It's a free parameter of this theory, but it's not. So it's a free parameter, but the same parameter appears here, here, and here, and here. So many couplings in this theory are all of the strength of A. And you may know that the Higgs boson was searched for about 50 years or something. Higgs's paper was in 1964 or 65. And the Higgs boson was only found about 12, 13 years ago. And the biggest problem was that although this is not the standard model, it's similar in the standard model. This number we certainly know. Okay, this is a coupling, this is the charge quantum, so we know it. But this number we have no idea, it can be anything. And this is why it was so, it's an independent number which gives the mass scale. And so we really don't know, didn't know what mass it should have until finally it was found by scanning all possible mass ranges consistent with other experiments. Yes.
In the last class, we also decomposed phi instead of as Rx and theta x
Yes.
as the real and imaginary part.
Yeah.
In case we do that same analysis here, do we reach a similar?
Good question. So you'll reach some sort of conclusion. I think what you'll find is that there will be a mass term, but that analog of theta, which is your imaginary part of eta or whatever, will linger in some other terms and leave you very confused. So that analysis is good up to quadratic order. Now actually some textbooks like Peskin and Schroeder take a very strange point of view. When discussing global symmetry, they do it in the Cartesian coordinates. That is, field is phi1 plus I phi2 and phi1 is expanded about A. But when they do Higgs mechanism, then they suddenly remember the R theta parameterization of phi. The way I've done it, R theta parameterization is always the one which shows you the correct feature of the Goldstone boson. Namely, it is the excitation around the circle of minima. Okay, and since that is also the circle around which gauge transformations act, because we say phi goes to e to the I theta times or I lambda times phi, that means it's a phase in that same circle. So that's why the gauge field is able to absorb the Goldstone boson. So that excitation isn't there. In fact, I'll make some comments about this now. So remember I said there's a key difference between global and local or gauge symmetry. So in global symmetry, which is the case we were discussing in the last few lectures, where phi simply transforms by a constant phase. Then two configurations related by symmetry are distinct, physically distinct, but have, what's the word? But they are related by symmetry. That's no better way to say it. But related, but have the same physics. I explained it to you a few minutes ago. Okay. Local symmetry. So two configurations related by symmetry. Are the same configuration. It's just two different descriptions. They are identified. People sometimes ask, what does it mean to identify things? So I'll give you a simple mathematical example of identification. You are aware that whenever the clock crosses 12 o'clock, miraculously instead of becoming 13 o'clock, it becomes 1 o'clock. And you have accepted this all your life. You did not fight with your parents when they told you this, I'm quite sure. Well, that's because on time we have imposed an identification modulo 12 hours. So every 12 hours, by convention, we just repeats. And every 24 hours, which is a more natural identification, that's because that's how the Earth's rotation is. And so daylight repeats every 24 hours. And so it's natural to choose this modulo 24 identification of the clock. But truly 12 o'clock today and 12 o'clock tomorrow are not the same time. We can say it's the same, I'll meet you at the same time tomorrow, but it's the same time plus tomorrow. It's not the same. Okay, so we can always impose an identification. If we didn't do that, time is just linear. It just ranges from minus to plus infinity as far as we know. But with that, time only ranges over 12 or 24-hour cycle. So it's the same thing here. We identify two configurations related by gauge symmetry and we simply say they are the same. Okay, that's the only the only meaning you can give to gauge symmetry, because gauge symmetry depends on an entire function. So that function has as much information in it as one entire scalar field. And in fact, today we saw an example beautifully. It's that symmetry which enabled us to take away a full scalar field from the theory. Okay, but supposing we had not done this calculation leading to this Lagrangian, just from this information which we discussed long ago, you could have predicted one thing, which is that in this case, there is spontaneous symmetry breaking. And so there's a circle of minima, all related. They are distinct, all the points on that circle are distinct, but they have the same physics. But in gauge symmetry, that same circle is a circle you can travel using gauge transformations, and those are not a symmetry but a redundancy. So actually all points on that circle are the same point. They are not distinct points. So we shouldn't have a Goldstone boson. When there's gauge symmetry, you can right away say there should not be any Goldstone boson, because it's the excitation around that circle, and that circle is now being identified by gauge symmetry. So there should not be any Goldstone boson. And in fact, after doing the calculation, we found that's correct. It would have been meaningless to have a Goldstone boson, because in fact, not only there should not be any Goldstone boson, but no symmetry is broken. Well, or let us say gauge symmetry is not broken, not spontaneously broken. Because, why would it be broken? Because we picked one point on the circle of minima as our choice of vacuum, but that's the same point as all other points on the circle. By gauge symmetry, we never did anything to break the gauge symmetry. It's not broken. That's why it's still there. Okay? There was a global symmetry, and I told you once how to distinguish global from gauge in the same theory. In the gauge theory, there's a global symmetry. That is the one where theta is constant all the way up to infinity. And the gauge symmetry is where theta depends on x, but its dependence dies out at infinity. So it's that second one, the gauge symmetry, which is not broken. Okay? Even then, people use the language spontaneously broken gauge theories. That's a very common language. It's just wrong, but people use it. Maybe even I use it sometimes. But it's not correct, because spontaneous breaking itself it's not the same meaning, though it's a similar calculation. Here it's actual spontaneous breaking, and here it is a process which all happens together. It appears spontaneously broken, a Goldstone boson appears, but it immediately disappears by a good choice of gauge field, and so at the end it's not there. So that means it was never there. So nothing was broken and no Goldstone boson is there. And so the correct expression for this kind of behavior is the Higgs phase. So we say that a gauge theory can be realized in the usual phase or the Higgs phase. In the usual phase, the vector field is massless. In the Higgs phase, the vector field is massive. To get the usual phase, I should couple the gauge field, keep it uncoupled or couple it to a potential which alone has no spontaneous breaking, like it has its minimum at the origin. Then I'll get a gauge theory in the usual phase where the gauge field is massless. If on the other hand I couple it to a spontaneously broken scalar theory, then the coupled theory doesn't have spontaneous breaking. Instead, it develops a Higgs phase. It just goes into a different phase. It's a different phase of the same theory. In both phases, gauge symmetry is realized. In one case, it's realized in the usual way. In the other case, it's realized in the Higgs way. It's just a non-trivial way, but it's there. Yes.
So when we were doing this entire derivation along the lines of the spontaneous previously, in this case we found out that there is this cross term, quadratic cross term, but we chose to only think of this Lagrangian with what actually exists, because this does not have those cross terms.
Yes.
But
we can choose any of them. All of them we can quantize. We'll just get the same answer. It'll just be more work. What would happen in all the other Lagrangians which have a theta and a cross term is that I told you just now, the operator O would be non-diagonal. Diagonalizing it is the same as removing theta, basically. That's all there is to it. If we diagonalize it, we'll find that there's a zero eigenvalue in that matrix, and that amounts to the absence of theta. So in general, it's simply in a non-diagonal frame, and that non-diagonal frame, then nobody says a non-diagonal frame is bad. It's just the least, not a convenient frame to analyze the degrees of freedom of the theory. Since there's always a zero eigenvalue of that operator, it means that at least one out of the 5 fields, a, mu and theta, isn't there. Which one it is, we can choose. We could choose one of the components of A to go away and keep theta. Okay, but the couplings are such that there would always be a massive particle in the spectrum. and there would never be a massless particle. It's very subtle, and actually after Higgs published his paper and also Braut and Engler, so all of them got the Nobel Prize except Braut passed away unfortunately, so Engler and Higgs got the Nobel Prize. And then Kibble and others developed the mechanism in much more detail. There was a lot of beautiful papers in '65. Interestingly, they didn't try to make any model of physics out of it. They just said, here's a phenomenon which might be useful to understand weak interactions. Namely, with gauge invariance and mass of a vector particle can coexist. Meanwhile, it was for 2 years more, it was more or less ignored by most of the other people who had been trying to understand weak interactions. In a way, you might say Higgs and Braut, Engler, they were more quote-unquote theorists rather than phenomenologists. They found a phenomenon and they were happy with that. They didn't try to fit it into a model that has direct experimental outcome. But people like Li and Yang were instead doing phenomenology, and they weren't paying much attention to this. Even though finally these people used the Yang, so tomorrow we'll discuss the same thing with Yang-Mills theory. What will we do in Yang-Mills theory? You can work it out on your own without any book. We'll couple an ON or UN vector model of scalars to a Yang-Mills ON or UN gauge theory, and we'll make that ON or UN, whatever it was, from global to local, and something will happen, and we'll get some multiple Goldstone bosons will have to disappear, and multiple vector fields will get a mass. That's what actually is realized in the standard model. Anyway, coming back to these people, it was only in 1967 that 2 years later that Weinberg wrote a paper called The Theory of Leptons, which more or less, with many details, some details missing, was a kind of final standard model theory which incorporates the Higgs mechanism. It was like the last ingredient in the theory, and he realized that it was. Salam had been doing similar things, but he never published his work. So but there was some unpublished conference talk which had some similar ideas. And Glashow did not participate in this part of the discussion. He, early in 1962, he simply tried out adding a mass term to this without asking the question that when gauge invariance is lost, how can we have a consistent theory? And so he had the right idea, but he didn't have a way to preserve gauge invariance along with the mass term. Now, I haven't shown you yet that this theory is consistent, but you can, there are detailed discussions in the literature, we might not have time to cover it, which say that because the underlying gauge invariance is present, this theory when renormalized, which we'll discuss after a few lectures, or this theory when quantized, doesn't have the A0 component in it because of the hidden gauge invariance, and therefore it is actually unitary. It doesn't have the problem of normal massive gauge theories.
So when you say consistent, you mean like absence of negative norm states?
Exactly, that's right. All this rigmarole was necessary, otherwise there would have been negative norm states. If we just considered these two terms and none of this, and then took these arbitrary, there would be negative norm states. Even if I simply change these numbers independent of each other, there will be negative norm states. Only in this particular combination, I can say, well, it comes from a gauge theory, and therefore it has no negative norm state. Then I can prove it from this Lagrangian directly.
Sir,
Yes?
this mu is taking part as a weak interaction.
Yeah, so it's not, because this is a U1 model. If I do this with SU2, then there'll be 3 AMUs, and those would be the weak interaction.
Then why you are saying eta is a Higgs field, like what its role?
Yeah, so this is a toy model with a toy Higgs field, and there's a massive photon, you might say, in this model, which is an analog of W boson. It's not a real W boson. Tomorrow we'll discuss the
analog of eta will play what role?
Analog of eta is the actual Higgs boson.
Okay.
So tomorrow also there'll be a Higgs, in the non-abelian case also there'll be one Higgs boson. For, let's say, SU2 breaking to nothing. There'll be one Higgs boson and 3 Goldstone bosons, which will be eaten by 3 gauge fields, which will become massive. And those roughly would be the W plus, W minus, and Z bosons that are known from experimental physics that were discovered. Not exactly, because unfortunately the standard model is based neither on U1 nor on SU2, but on SU2 cross U1. And the pattern of symmetry breaking is more subtle. SU2 cross U1 breaks to U1. So that last, I'll discuss it tomorrow. I don't know why I'm doing it now. We are way over time. Chalo, let's stop. Yeah.
One more topic.
Yeah, tell me what. Yeah.
So we are basically starting with the Lagrange and having some nice symmetries.
Yes.
Then we are seeing that the minima is somewhere else.
Yes.
And we are shifting it.
And we have to do that, to do
but
path
it's a-
integral. Yeah.
But the nature is not breaking any symmetry spontaneously. It's our way of getting some Lagrangian to.
No, without the gauge field, this nature is breaking a symmetry spontaneously. It's with the gauge field. The symmetry is not a global symmetry, but a gauge invariance. So it's a redundancy.
I
So
could
then
have
nature is
started
not
with this
breaking.
Lagrangian from the start.
Well, you would have never come to this Lagrangian with all these coefficients correlated. Now people, of course, argue that, yeah, you can start with that. You can start with the quadratic part, what you want, and you can build up these terms by unitarity. But that's not a way anyone would have discovered it first. It's easy
No,
to say now.
It's a way of discovering, but
Yeah.
I'm saying that
Yeah.
the nature is not breaking any symmetry spontaneously.
In this case, there was no symmetry. There was only gauge invariance. That's not a symmetry. Actually, if you separate the symmetry into two parts, the gauge symmetry which falls off at infinity and the global symmetry is broken spontaneously. It doesn't affect the gauge field at all. It doesn't participate in the global symmetry. That is broken spontaneously. The local symmetry cannot be broken. It's just a local symmetry. Yes.
The global symmetry would still produce Goldstone bosons?
No. So that's the point. It doesn't. And why it doesn't? Good question. Yeah, let me think about that. It doesn't. There are no Goldstone bosons in this theory. We have seen explicitly. And that's a theorem.
So we have proved that for the gauge field, for theta x it does not exist, but for the global symmetries, seems like if we follow the same procedure as before it.
Yeah, let me think about it and give you a more convincing answer tomorrow.